Hello, everyone. This is the last topic that we want to discuss in training models. It is logistic regression. So far, we studied linear regression, gradient descent perspective linear regression, polynomial regression, and regularized linear regression that try to reduce the overfitting problem with potential overfitting problems with linear regression. And now we are moving to a different category of linear regression. Is called logistic regression. Let's quickly review what is a linear regression. So now you should be very familiar with this function form. That is, you use a linear model to predict the y value based on different features of x1 all the way to xn with parameters of theta 0, theta 1, all the way to theta n. And then you could use theta dot x to be the vectorized form, to be the predictor for y. In linear regression, we're trying to find a theta that would be able to minimize this quantity, mean squared error, MSE. So what is logistic regression? It's also called logit regression. It's commonly used to estimate the probability that an instance belongs to a particular class. For example, what is the probability that this email is a spam? What is the probability that this customer is going to purchase this item on Amazon after collecting some other links, that's relevant links related to this item, things in that nature. So essentially, if a dependent variable is not continuous variable rather than a probability, then you want to leverage logistic regression. If the estimated probability is greater than 50%, then you could relabel the class to be 1, positive class. And otherwise, it predicts that it doesn't. It belongs to the negative class labeled as 0 when the probability is less than 50%. In that case, it becomes a binary classifier. So instead of probability regression question, you could even transform it to a binary classifier. Of course, you could always set up different threshold so that it could potentially even become a multi-class classifier. Let's look at this function form for logistic regression. So this probability estimate is a sigma function, sigma of theta transpose by t. This sigma function turns out to be a logistic function. Sigma t equals to 1 over 1 plus exponential of negative t. It happens that this logistic regression actually follows this function form. You can see that on the left-hand side, it's approaching 0, and on the right-hand side, as t increase, is approaching 1. The cost function for logistic regression is having this form is also called log loss. So if it's yi, and then you use yi times log predicted value of p for this instance plus 1 minus yi and log of 1 minus predicted probability for this instance. And in general, this would be something we call it log loss in logistic regression cost function. The bad news is that there's no known closed form equation to compute the theta that would minimize this cost function. In other words, there is no equivalent of the normal equation in linear regression. In linear regression, you're able to find that closed form to estimate theta. But in logistic regression, we're not able to figure it out by closed form to estimate that theta. Good news is you still can consider the problem from the gradient descent perspective. The function turns out to be convex, and the gradient descent is guaranteed to find the global optimum, in this case the global minimum, if the learning rate is not too large and you wait long enough. The model converges, you find the global minimum. Let's introduce another dataset. This dataset is called iris flower dataset. It's something that we're going to use throughout the rest of the learning journey of machine learning. So you should know it. So it's 150 iris flowers with 3 different species. One of them is called iris setosa. The other one is called iris versicolor, and the third one is called iris virginica. And then it actually have 4 dimensions to differentiate those 3 types of flowers. One is petal length, second one is petal width, third one is sepal length, and the fourth one is sepal width. So essentially you want to look at the petal and look at length and width, and also sepal, look at the length and width. So here we use this iris flower to build a logistic regression model. Specifically, we want to differentiate between iris virginica versus not iris virginica. And then we leverage this particular dimension, that's petal width. So you can see that this petal width in general looks like the petal width for iris virginica is actually wider compared to the other 2 types of flowers. So if you build a logistic regression and then try to plot the probability of iris virginica versus not iris virginica, you can see that the graph look like this for iris virginica. Now it turns out to be an important decision that you need to make. That would be the decision boundary. Where would be your proper decision boundary to help you to make a decision? Because if this decision boundary is too much on this side, apparently some of this would be misclassified as not iris virginica. However, if this line is actually too close to this side, you're running a risk that these points are classified as iris virginica. Unfortunately, these points are actually not iris virginica. So it's kind of a trade-off, right? Now, in this case, we actually have something called decision boundaries. So it essentially says, what's the decision boundary between the iris virginica versus not iris virginica? Of course, there would be a probability attached to this all these decision boundaries. For example, this particular one says, if we use this decision boundary, anything that's on this side would have 90% probability to be iris virginica. And on the other end, if you use this boundary, some of this would only have much smaller probability. One interesting thing that you should be aware here is, just like other linear models, logistic regression models can be generalized, regularized using L1 or L2 penalties. Scikit-learn actually automatically adds L2 penalty by default to regularize the model. Now let's move on to another extension of logistic regression. This one is called softmax regression. Often cases people actually also call it as multinomial logistic regression. Essentially, it can be generalized to support multiple classes directly without having to train and combine multiple binary classifiers. So the idea is simple. When given an instance of X, the softmax regression model first computes a score, skx. This skx is for each class k because we want to estimate what this instance class is. In that iris flower example, it will have 3 different classes, and then let's calculate that s1x, x2x, x3x for each instance of x. And then you estimate the probability of each class by applying the softmax function, which is also called normalized exponential function, to the scores. So once you calculate those 3s score for each instance, it would have s1x, s2x, and s3x, and then you try to calculate the probability based on each of the s1x, x2x, and s3x to come back with p1 probability, p2 probability, and p3 probability. After that, you pick the highest estimated probability, which is simply the class with the highest scores. You pick the class with the highest scores, and then you say, okay, this one have a higher probability to be belonging to class 1 or class 2 or class 3. Okay, the model, the objective in this example is, in this case, is to have a model that estimates a high probability for the target class and consequently a low probability for other classes. So you leverage something called cross entropy cost function. It's very similar to what we just saw for logistic regression, and for each class k, you would have a specific yk and a corresponding probability estimate of belonging to that k log pk, and then this whole function is defined as the cost function for multinomial logistic regression, and correspondingly for this objective function, there would be an estimate for the gradient vector for specific class k that you can leverage. In scikit-learn, you could leverage logistic regression, just define multi-class equal to multinomial, and use LBFGS as a solver to estimate. And then once you have that, you would be able to fit, and then you can also predict a specific input. In this case, we only used the petal length and petal width, and then if the petal length to be 5, petal width would be 2. What is the output of the probability? Turns out to be which one is larger. You can see that 0, 1, 2, those 3 different classes, and then this one have the highest probability. That's why it turns out to belong to the index of 2 class, which is essentially the 3rd class, right? 0, 1, 2. Okay, that's scikit-learn with multinomial logistic regression. Similarly, you would have decision boundaries for multinomial logistic regression as well. One thing note note pointing out is this 0.3 probability. This 0.33 essentially says that there is an equal probability of belonging to one of the classes if you pick this particular decision boundary. Okay, this actually concludes our discussion of regression models in general. If you go back to the first slide, you should be aware that we discussed linear regression, gradient descent method for linear regression, followed by polynomial regression and regularized linear regression. On top of that, we even studied logistic regression. Logistic regression can be also applied to some classification problems. Okay, I'll stop here and thank you.